Previously, when we talked about matrix multiplication, we always talked about square matrices, whether it's 2 by 2 matrix or a 3 by 3 matrix. This time, we're going to talk about matrices that are not square matrices, which means the number of rows and number of columns of a given matrix would not be the same. So we'd like to see what happens when the number of rows and number of columns of a matrix are not same, and how do we multiply two such matrices that are not square matrices. So the first problem we're going to see is essentially about the dimensions. So to understand the dimensions or orders of matrices a little bit better in a situation where they're not square matrices. So for example, in this problem, they said if A is a 3 by 4 matrix, so this is clearly not a square matrix, they're not the same numbers, and C is a 3 by 6 matrix, not a square matrix, and A times B, so matrix A multiplied with matrix B produces matrix C, then what are the dimensions of the matrix B? So over here, given the dimension of matrix A and the matrix C, so we know the dimension of matrix A and matrix C, we don't know the dimension of matrix B, which is what we would like to find out now. Before we start solving this problem, let me give you an overview of the idea of the dimension or order of matrices and how that works in general, not necessarily in the square matrix case or the matrices that are not square. So this is the general idea, this is how it works. So this is applicable for both square matrices and the matrices that are not squares. So the idea here is that if we have a matrix 1, which is the first matrix, and matrix 2 is the second matrix, and the resultant matrix is just, call it matrix, then the dimension, if the dimension of the matrix 1, the first matrix, is row column, that's the dimension. By 1, I'm indicating this matrix. So row of the first matrix and the column of the first matrix. And this is the row of the second matrix and column of the second matrix. Now, we can multiply these two matrices if and only if these two number matches. So the number of column of the first matrix, by 1 I mean the first matrix, number of columns of the first matrix should match with the number of rows of the second matrix. If these two number matches, so if it is 3, it has to be 3, if it is 5, it has to be 5. So if these two number matches, only then we can multiply two matrices. Now, that's like a precondition, the eligibility check for matrix multiplication. Every time you multiply two matrices, you have to check it, otherwise you might make some mistakes, you don't know. Now that's the eligibility, so if they're eligible, we multiply them. But what would be the dimension of the resultant matrix? The row number of the resultant matrix is coming from the row number of the first matrix. So this row number of the first matrix will be the row number of the resultant matrix, and the column number of the second matrix over here, this would be the column number of the resultant matrix. This is how we can construct the dimension of the resultant matrix. That is the general idea, and this is applicable for matrices that are not even square matrices like R by C. So these two numbers are not the same, they're different numbers. If it is 2, it's 3, it's something like that. So now that we understand the general notion of the dimension or order of matrix, we can try to attack this problem. So according to the problem statement, we can write that the matrix A has dimension 3 by 4 and the matrix C has dimension 3 by 6, and in the case of matrix B, we don't know what it is. I just wrote it as an empty box, and we will fill this box according to this idea. So what is the row number for the matrix B? We learned that in order for two matrices to be able to multiply, these two number has to match. The row number of the second matrix should match with the column number of the first matrix. So the row number of the second matrix should match with the column number of the first matrix. So this is the column number of the first matrix, which is 4. If the column number of the first matrix is 4, then we can infer from here, according to this idea, that the row number for the second matrix should also be 4, because this is 4. They have to be exactly same. So I can write that this number should be 4. Let me write 4 over here. Okay. And then looking at the construction of the dimension of the resultant matrix, we can see that the row number of the resultant matrix is coming from the first matrix. The row number for the resultant matrix is 3, and we can see it's coming from the first matrix, row number of the first matrix, according to this idea. So this is 3, this is also 3, which means it's coming from the first matrix. Now the column number of the resultant matrix should come from the column number of the second matrix. So the column number of the resultant matrix in this case is 6, and this should come from the column number of the second matrix, which is B in our case. So this is the column number of this second matrix. This column number should come from here. So if this is coming from here, they should be exactly same. So this number should be 6. So the dimension of the matrix B is 4 by 6. So I can write, therefore B is a 4 by 6 matrix. So we just solved the first problem. Now we'd like to solve another problem. So let's go ahead and try to solve another problem. What we like to do here is we like to find out the product of these two matrices. We want to multiply these two matrices, and looking at the dimension of the matrix, this is 4 by 3 matrix. It has 4 rows and 3 columns. So it's a 4 by 3 matrix, and this is a 3 by 2 matrix. It has 3 rows and 2 columns. Now if you remember, we talked about the eligibility for multiplying two matrices, and the number over here should match with the number over here. These two numbers has to match. If they do not match, we cannot multiply. And this number matched is 3. This is also 3, so we can safely multiply these two matrices. The numbers colored in orange, these are the numbers. We'll construct the dimension of the resultant matrix. We don't know yet. After all of this calculation, we will see if that matches. So we anticipate that the dimension of our resultant matrix will be 4 by 2. Now let's try to multiply these two matrices. The idea of matrix multiplication will follow the same procedure as we discussed in the previous lecture. So what we do is we select the first row and then we select the first column. So this row will get multiplied with this column. Essentially it's a dot product of this row and this column, and then that produces this. So entry 4 will get multiplied with 7, 0 will get multiplied with 0, 2 will get multiplied with -1, and you sum them up, this is what you're going to get. Afterwards, what we do is we select this second column. The row will not change until it ends up hitting all the columns. So this time we select the second column, and then we take the dot product of this row with this column. So that produces this, according to the same procedure. And then, since we're done with hitting all the columns that are in here, now we can change row. So we go back and select the second row. This is the second row, and it will hit the first column over here. So essentially what we're going to do again is we're going to take the dot product of this row with this column, and then that produces this. And next, this row will hit this column, and again we take the dot product of these two selected row and column, and that produces this number right over here. And then we move forward and select the third row. So this third row will hit this first column, and that produces this number. And then we move forward and change our column from the second matrix. So this selected row will hit the second column, and that will produce this number. And finally we will select the last row, which will hit this first column, and that will produce the dot product of these two will produce this number right over here. And then we will change the column, because this selected row will hit the second column now, and that will produce this number right over here, which means we are done with multiplying two matrices that are not square matrices. So these two matrices, none of them were square matrices, and we were successfully able to multiply because they were eligible for multiplication. So since we multiplied following the same procedure, each time you select one of the rows, that row will hit all the columns, and that will keep producing the entries for that selected row, and that's how we will proceed. Now, all you do is you just simplify it a little bit, a bunch of multiplication and summation, and then afterwards this is what you get. This is our resultant matrix, and it looks like it has the dimension 4 by 2. So it has 4 rows and 2 columns. So it's a 4 by 2 matrix. And we anticipated previously, I matched them with the same color, the orange color. So the number that are in orange over here, we anticipated that that will produce the dimension of the resultant matrix 4 by 2. And we found that yes, it is 4 by 2. So we just solved this problem. All right, so see you in the next lecture.